Welcome students to my YouTube channel. In the last class we have solved the example 9.1. Today we are going to solve the example 9.2. A copper wire of length 2.2 meter and a steel wire of length 1.6 meter, both of diameter 3 millimeter, are connected end to end. When stretched by a load, the net elongation is found to be 0.70 millimeter. Obtain the load applied. Okay, we are drawing this diagram. Here we are considering the length of the copper wire and this is the length of the steel wire. We are applying a mass M. See, this is the mass M. Okay, as soon as we apply a mass M, what will happen is that this wire will become elongated. It will increase its length. So this will be the change in length of the copper wire plus change in length of the steel wire, and this net elongation is given to be 0.70 millimeter, or we can convert it into meter as 7 into 10 to the power minus 4 meter. That this net elongation 0.70 millimeter, and this we can write as 0.77 into 10 to the power minus 4 meter. Okay. Next we are going to see, can you state the statement for what is the Young modulus? The Young modulus is given by stress by strain, or stress is equal to force per unit area and strain is given by change in length to the original length. Now if we consider this Young modulus for a copper wire, then we can consider this to be this like this. Similarly, we can consider the Young modulus for steel wire as force per unit area divided by del L of S by L of S, and we can write this to be del L of C by L of C is equal to, we can cross multiply this, it is equal to force per unit area, or force per unit area is given as Young modulus of steel into del L of S by L of S. Okay, this is the change in this force per unit area. This force per unit area will be same for the copper and the steel wire, because we know for the area we know they have the same diameter and the diameter is given to be 3 millimeter. So the radius will be same, or the area which is given by pi r square. The area of both the copper wire and the steel wire will be same because they have the same diameter or the same radius. So we can say that area is same. Similarly, force, okay, the force will also be same for copper wire and force of the steel wire, because you see force is equal to mass into gravity, acceleration due to gravity, or we can say the same load is applied along the wire. As the same load is applied along the wire, therefore the mass is same for copper and steel wire, and the acceleration due to gravity is also same, or we can say that the force is also same for both the copper and the steel wire. Therefore, we can say that force per unit area for both the copper wire and the steel wire is equal. Or we can also write this equation as force per unit area is equal to Young modulus of copper wire divided LC by L of C is equal to Young modulus of steel wire into del L of S by L of S. Or okay, we are writing this from here, and force per unit area is same, therefore we are writing this as like this. Or we can write this to be, okay, we can write this equation in a simple form like force per unit area is equal to del L of C. We are bringing this del L of S, that is the change in length of the steel wire, is equal to Y of S by Y of C multiplied by del L of S by, okay, we are considering Young modulus of steel wire, that is given as 2 into 10 to the power 11 Newton per meter square. We are not writing Newton meter square. And for the Young modulus of copper wire, it is already given in this page. Okay, you check this page. Young modulus of copper wire is 1.1 into 10 to the power 11 multiplied by del L of S, that is the change in length of the steel wire. Oh, I have wrote this. This will be equal to, because we are writing this del L of S, we are taking in this side, therefore this will be L of C by L of S. We are taking this one this side and this one this side, so we can write this L of C, length of the copper wire, that is given to be 2.2 meter. Here it is given the length of the copper wire is 2.2 meter and the length of the steel wire is 1.6 meter. 1.51 divided by 2.1, so we get 2, and 10 to the power 11 we are cancelling them, or we can write 4 divided by 1.6, or we can write this to be equal to 2.5, or we can write del L of C by del L of S is equal to 2.5, or we can write this to be equal to del L of C is equal to 2.5 del L of S. Okay, the net elongation that we have already written, this one, del L of C S plus del L of C is equal to 7 into 10 to the power minus 4, or we can write this to 2.5 del L of S plus del L of S is equal to 7 into 10 to the power minus 4 meter, or this we can write 3.5 del L of S is equal to 7 into 10 to the power minus 4 meter, or we can cancel this to be, or del L of S is equal to 2 into 10 to the power minus 4 meter, or del L of S. We can cancel this and we are getting this value. Okay, now what we are doing is that we are trying to place this in the in this equation. We can place this in this equation, or we can also place this in this equation also, in order to find the force. Here we are considering to calculate from this equation, or force per unit area is given as, what we need to calculate, the obtain the load applied, that is the load applied is equal to force. Okay, so we need to calculate the force, so we are calculating force per unit area is equal to Young modulus of the copper wire into L of C, or force is equal to Young modulus of copper wire into area into del L of C by L of C, or we can calculate this easily. Young modulus of copper wire that we have written 1.1 into 10 to the power 1.1 into 10 to the power 11 multiplied by area pi into r square, so r square will be 1.5 into 10 to the power minus 3 square multiplied by del L of C, that is we can write this to be, okay, for calculating del L of C we need to calculate del L of C, which is given as del L of C is equal to 2.5 del L of S, 2.5 del L of S, and we have already calculated here del L of del L of S here. Okay, so we have written down del L of C is equal to 2.5 L of S, or 2.5 into del L of S we have already written that to be 2 into 10 to the power minus 4. Okay, 2 into 10 to the power minus 4, or we can write this 5 into 10 to the power minus 4. So multiplying it with 5 into 10 to the power minus 4 divided by change in length of the copper wire, original length of the copper wire, that is given to be 2.2, and if we calculate this equation, then the answer will come to be 176 Newton, approximately 176 Newton. Thank you for watching this video. Hope you like this video, and please subscribe to my channel so that I can keep you updated about this. We are going to solve equation example 9.3 in the next video. Thank you.